In this lesson we're going to look at circles and properties of circles. There's really an enormous amount of material that we could cover here, so I really just want to cover some of the most important properties and the basics. So if a little bit of terminology first. If we draw in the center here and we connect the center to any point on the circle, call that the radius, and that's usually symbolized with an R, so we could have another radius going in the other direction. And if we have the two radii lined up, we have a line segment going all the way across from one point of the circle to another through the center. That's called the diameter. So the diameter is just simply twice the radius, so that's an important relationship. The diameter is 2r, and we can use this in various formulas. The perimeter of a circle is usually called the circumference. We don't use the word perimeter with a circle for some reason. We just simply call it a circumference. And the formula for the circumference of a circle is pi times the diameter. In fact, it is in some sense the definition of pi. Pi is the ratio of the circumference of a circle to the diameter of a circle. And since the diameter is just twice the radius, we can also write this as 2 times pi r. Now, pi is an irrational number, meaning that it can't be expressed as a decimal or a fraction exactly. The decimal approximation for pi starts off with a very familiar 3.14, goes on 159, etc., and would go on forever if you wanted it to. You don't really need to remember any of the digits of pi. If you are going to approximate it without a calculator, in a lot of calculations, a good enough approximation is just simply thinking of it as a bit more than 3. And that will often allow you to distinguish between answer choices that are perfectly reasonable and answer choices that are completely unreasonable. So just keep that in mind. You often don't need anything more than a little bit more than 3. Now, the area of a circle is pi times the radius squared. And if you go back to that circle we just had and you imagine drawing in 2 more radii, you can actually think of creating a bounding square, and each of the quarters of this square has an area of r times r, or r squared. And so the bounding square is 4r squared, and the circle is just pi r squared. So the circle occupies a little bit more than 3/4 of the square that the circle is inscribed in. Alright, let's take a look at some other properties of circles. So let's imagine we have the center of the circle, and we have 2 radii drawn. The angle formed by those 2 radii is referred to as a central angle. It has as its vertex the center, which is usually symbolized with an O, and let's label the 2 points on the circle as P and Q. So we've got an angle, angle POQ, which is a central angle. And let's say that it has a specific measurement. We'll just call it x degrees in this case. Well, what if we wanted to know how long the arc between P and Q was? Now, if you look at the point P on the circle and the point Q on the circle, and you say, well, the arc PQ, it's actually ambiguous. There's 2 possible arcs. You could think of going from P to Q the short way. That's known as the minor arc. So the minor arc, PQ, is usually the one that we're going to be looking for. But the long way around is called the major arc, PQ. And sometimes an additional point is indicated on the circle just to make it more obvious. But if it's not specified, you can assume it's the minor arc. So if we want to find the length of that minor arc, PQ, well, a full circle is 360 degrees. So if you added up all of the central angles, you would get 360 degrees, and therefore the arc PQ is a fraction of the circle, and the fraction is defined by whatever the central angle x is divided by 360. And then the circumference is either pi d, or if you're given the radius, 2 pi r. So it's that fraction times 2 pi r. So if we let x equal 60 degrees, for instance, then we're dealing with a fraction of the circle, 60 over 360, which is 1/6. And let's say we imagine the radius is 12, so we have a radius equal to 12. It's going to be that fraction times 2 times pi times 12. So that's 1/6 times 24 pi, which is going to be 4 pi. Now, normally when you have pi in your calculations, you leave the answer as a multiple of pi. That's really the only way to express that number exactly. 4 pi is an irrational number. What is it approximately? Well, you know that pi is a bit bigger than 3, so 4 times 3 is 12. 4 pi is therefore a little bit bigger than 12. And if you want a decimal approximation that's better than that, you can pull out a calculator and plug away. But the only way to actually exactly represent it is just simply to leave it as 4 pi. Alright, let's take a look at some more properties to do with angles. If we have a circle with a center and we draw in the 2 radii, we've already referred to that angle formed as a central angle. If I connect another point on the circle, I'm going to call that R, to these 2 points P and Q, these lines are called chords. So a chord is a line segment that connects 2 points on a circle. And these 2 chords form what is known as an inscribed angle. And the ratio between the central angle and the inscribed angle is 2:1. That central angle is double the inscribed angle. So if we know that the central angle has a measure of x degrees, then the inscribed angle has a measure of x over 2, half that. So we can write this out. Angle POQ, the central angle, is equal to angle PRQ over 2. So PRQ is an inscribed angle. Now there's nothing special about the placement of R. So you can imagine rotating R around the circle. You could move it up, you could move it down, and it's not going to change the angle, which is an interesting property of the circle. If you brought the point R all the way around so that it was in between P and Q, then you'd have a difference. But if you leave R on the other side of P and Q, in other words where it is now, and just don't rotate it beyond P and Q, then this ratio is always going to be constant. And so that angle, that inscribed angle, is actually not going to change as you move R around the circle. Now, I said a minute ago that PR, that line segment, and RQ or QR, these are known as chords. And the longest possible chord in any circle is the chord that passes through the center of the circle, and that's simply the diameter. So the diameter is a chord. So the longest chord is the diameter. The radius is not a chord because it doesn't connect 2 points on the circle. It only connects the center of the circle to 1 point. Now, we can also say that both the central angle and the inscribed angle contain, or a more technical word for the same thing, subtend this arc PQ. So they both contain or subtend that arc PQ. And actually we also sometimes refer to them containing the chord PQ. Alright, and so another property is that if a central angle contains a chord of a given length, then any other central angle containing a chord of the same length will be the same central angle. Or similarly, an inscribed angle containing a chord of a given length will be the same as any other inscribed angle containing a chord of a given length. Now let's use that property of the ratio between the central angle and the inscribed angle to explore what happens when you inscribe a triangle inside a semicircle. So if you have the diameter drawn, that's a semicircle, but we can think of this as a central angle. All right, we have 2 points on the circle, and you can think of the center of the circle there as a vertex. So we've sort of expanded this central angle to be all the way half a circle, 180 degrees. Well, any inscribed angle then with the same 2 endpoints will have to have an inscribed angle of half of 180 degrees, which is 90 degrees. In other words, a right angle. So any triangle inscribed in a semicircle is a right triangle, as long as one of the sides of the triangle is the diameter. So any triangle inscribed in a semicircle is a right triangle. So that's a very important property, and that comes up in a variety of problems. Let's take a look at what happens if you have a tangent line. So a tangent line is simply a line or line segment that touches the circle in one point. So it doesn't cross through the circle, and it doesn't miss the circle altogether. It touches it at a single point. That point is referred to as the point of tangency. Now if we connect that point of tangency to the center of the circle, that will always form a right angle. So this tangent here and the radii, or the radius, forms a right angle. And this is a property that, again, will come up quite frequently in different problems. What if it doesn't, what if we're not trying to form an angle between the point of tangency and the center? So what if we have a tangent line and a chord? So we've got an angle there formed by the line of tangency and a chord. Well, what can we say about that? Well, it turns out that the inscribed angle, any inscribed angle containing that same chord, is going to have the same measure as the angle between the chord and the tangent line. So this angle is equivalent to that angle right there. Now you can see that by drawing in those 2 other chords, I've actually created a triangle that's inscribed in the circle. And in fact, I've got another inscribed angle over here that is equivalent to a different angle between the tangent line and a chord. And now if you look at the diagram, you can see some nice symmetries, because within the triangle we have 3 angles. And we know that the 3 interior angles in the triangle add up to 180 degrees. So I've got the angle marked with a single dash, the angle marked with a double dash, and the unmarked angle. They add up to 180 degrees. Well, looking along the tangent line, I have a straight angle, which also adds up to 180 degrees. And you can see the same 2 marked angles and the same unmarked angle. And so we have this nice symmetry. So this kind of diagram, these properties don't show up very often, but if you're looking at some of the more advanced geometry questions, this sort of thing is very, very useful.